transverse mechanical waves in the last lecture, and we saw the relationship between tension, linear mass density, and wave speed, and also the various terms like angular frequency, wavelength, etc. So, very important part of the analysis of waves to understand the mathematical framework on which the wave equations are written. So let's take a review quickly of these things from last lecture and then continue onwards today to understand further physical properties of waves, like the power transmitted through a wave, that is the mechanical energy transmitted per unit time through the propagation of the wave. And then also from there onwards, we will study about superposition of waves. So anyhow, let's begin. So in fact, what we will start with today is that so far we have seen transverse mechanical waves, one-dimensional transverse mechanical waves traveling on a string, and that too of the harmonic variety. That is, the source of the wave is a harmonic oscillator. Hence, the wave shape is a sine wave, and the oscillation of the medium particles is a simple harmonic motion. Now, today we will slightly generalize that aspect to begin with. Okay, so transverse mechanical waves. And as part of that, we have seen the one-dimensional harmonic transverse waves on a string. So the equation of the wave was a harmonic equation, which shows you the two interpretations, that if we freeze the value of x, then that will give us the simple harmonic oscillation of a particular medium particle along the y-axis with an angular frequency of omega and an amplitude of a. On the other hand, if we freeze the value of time, it will give us y as a function of x, which will look like a sine curve or a sinusoidal shape, which has a wavelength of lambda, which is given by this relation. Okay. And of course, the propagation speed with which this shape moves along the medium, that is omega by k or f lambda. But also to remember that the propagation speed is a property of the medium's physical state, that is
linear mass density
and linear mass density. Yes. So tension is like a elastic sort of property. It determines the amount of tension, determines the elasticity in the string, and linear mass density is to do with inertia. So it depends on these two factors. Okay. And when we have this relation V is equal to F lambda, so in this we understand that V is a property of the medium. It depends on the medium's properties. F is the property of the source, the simple harmonic oscillator that is creating this disturbance. So lambda becomes dependent on both the source and medium's properties. Okay. So we will continue from that point onwards today. First of all, by understanding power transmitted along a 1D harmonic wave. That is the average energy transmitted per unit time along the string. Power is equal to the average rate of propagation of mechanical energy along the medium. So in this case, the medium is the string, which is basically the x-axis. So this power can be understood as dE by dt or delta E by delta t, whatever average value of that. Okay. So we will see how to determine this quantity. And of course, our knowledge of SHM will come in very handy over here. So looking at the medium as a string which is under a tension T and has linear mass density mu, infinitely long string x going to infinity on that side. So if there's a wave propagating along the string such that the wave travels like this at a speed of square root T by mu. So now consider any section of the string like this, see, which is of length dx at a distance x from the origin. So this section is like a differential element dx. It has a mass dm which is which is mu, that is linear mass density into dx. Okay, so this is the mass of that section. So this section, this dm, is under SHM, okay, with amplitude equal to a and angular frequency equal to omega. So therefore, it has a kinetic energy at any instant which is half dm into del y by del t whole square. Okay. So actually, before we come to this discussion, let's also discuss about. I will just take this forward a little. First, we will discuss about particle velocity. Okay. So this del y by del t that I've written here. Let me explain this term first. Then we will come back to this. Okay. So another important set of physical properties we'll study. Then we'll come back to this power transmission concept. And that is, having understood the equation of the wave and all that, we will see how to determine what is called particle velocity and acceleration for any particle on the medium. That is, in this case, that will become, this particle on the medium will basically become a differential section dx of mass dm equal to mu dx on the string. So same diagram actually, as the wave is propagating through the string like this, the medium particles are oscillating up and down. So as the wave is propagating like this, you can see that, so any medium particle, it is basically doing this kind of motion. It is going up and down with an amplitude of a between y equal to 0, y equal to a, and y equal to minus a. So we take any section of the string which is of length dx like this, that particle, it has, so at any given point x equal to x on the string, the instantaneous displacement at time t its instantaneous displacement is given by this equation. So this is this point's instantaneous displacement. So therefore, its velocity will be del y by del t, that is partial differentiation of y with respect to t. Okay. That means treating x as constant. Okay. So partial differentiation of this function del by del t of A sine omega t minus kx plus phi. We'll just treat this like a regular differentiation, but as if x is a constant, because we are looking at a particular medium particle. So for us, the value of x has become fixed. So we are looking at that medium particle x equal to x is displacement y as a function of time. So now del y by del t represents this rate of change of that function with respect to time. So just differentiate this like you would normally do, treating x as a constant. So this whole term kx plus phi is like a constant minus kx plus phi. So the dependence with respect to time is sine omega t plus some constant. So the differentiation will be like this. A comes outside, derivative of sine is cos. So cos omega t minus kx plus phi, but into derivative of the term inside the bracket. So again, remember in the term inside the bracket, x is now a constant because we are partially differentiating with respect to time. So only omega comes in that derivative. So the particle velocity is given by this function del y by del t is a omega cos omega t minus kx plus phi. And like as expected for any particle in SHM, the maximum value of particle speed or particle velocity is a omega.
Yes.
And also that del y by del t is equal to plus or minus a omega at y equal to 0, and del y by del t is 0 at y equal to plus minus a. That is at the extreme position of oscillation it is having 0 speed, whereas at the mean position it is having maximum speed. So that is about particle velocity, and similarly we'll do another partial differentiation of this velocity with respect to time, so that will give us a partial acceleration, okay, or the particle acceleration rather, and that particle acceleration will again reflect the property that it's an SHM. So anyhow, just note down this part first, okay, particle velocity. We'll discuss particle acceleration next. So there's nothing very difficult or nothing very new over here. It is just like the velocity and acceleration of a particle in SHM. But only now our wave equation is y as a function of x and t, not just as a function of t, because it's representing the oscillation of a collection of particles in the medium, not one particular particle in SHM. So to isolate one particular particle at x equal to x and find out its velocity and acceleration as a function of time, we have to do partial differentiation. That's the only difference. Otherwise, it's the same derivation you've seen in SHM. Okay, and of course, we will need this equation of particle velocity in the next derivation we are going to do, which is about the power transmitted, because part of the mechanical energy transmitted is in the form of kinetic energy of the particles. Okay, now moving on to the next thing. So, and particle acceleration, secondly. That will become del 2y by del t square, and that will be derivative of the particle velocity, which is a omega cos omega t minus kx plus phi. So again, partial differentiation, a omega is a constant. Derivative of cos is minus sine. Okay. And then differentiation of this whole term inside the bracket. So you can see that we get that relation, that del 2y by del t square is minus a omega square sine omega t minus kx plus phi. So this also confirms the property of SHM, that the particle's acceleration along its oscillation axis, that is the y-axis, is proportional to displacement from the mean position and opposite in direction. So this is the dynamical condition of SHM with angular frequency omega.
Sir, that and particle acceleration, that what is that second in last? A omega?
Which one? A omega cos omega t minus kx plus phi. We are differentiating that. So it will become a omega multiplied with minus sine omega t minus kx plus phi multiplied by omega. Right?
Yes, sir.
Okay, so now let's come back to our original derivation we are doing for the power transmitted. Okay, so we want to calculate the rate at which mechanical energy is transmitted along this medium. So once again, if you look at a particle on the string, which is of mass dm, which is mu dx, it is under SHM with an amplitude A and a d omega by dt like this. Because if the wave propagating has an equation A sine omega t minus kx plus phi, let's say, then a particle has del y by del t at any point of time of A omega cos omega t plus phi, sorry, omega t minus kx plus phi. This whole thing whole square. So you can see one thing, that the maximum kinetic energy that the particle will have when it is at the mean position,
Yes, sir.
that will be when that cos omega t minus kx term, that becomes either plus or minus 1. So the maximum kinetic energy of such a particle will be this, okay, because del y by del t's maxima is of magnitude A omega. And from the property of SHM, the total mechanical energy of SHM of such a particle is equal to its maximum kinetic energy. SHM property, that is at mean position, kinetic energy is maximum and it equals to the total mechanical energy. So the total mechanical energy of oscillation of this particle is therefore this term. It is half dm or mu dx into a square omega square. Okay, so now we have to calculate the rate at which this energy is propagating. We have come to the energy of that single particle of mass dm equal to mu dx. Okay. But now, as the wave is propagating, the total number of particles which are oscillating is all the time increasing. The span of the wave, the value of x for which the wave is operating, is all the time increasing, because the wave is traveling at the rate v, which is dx by dt or delta x by delta t. So taking that into account, next we will see how to calculate the power transmitted or the rate of transmission of mechanical energy. Okay, so now the power transmitted is the rate of energy transmission. I can see here that dx by dt is nothing but the propagation speed along the x-axis. So this power can be written as half mu v omega square into a square, or it can also be written as half square root of tension into mu into omega square into a square, because we know that v is equal to square root t by mu. So importantly, power is proportional to square of the amplitude. So basically, again, we have to understand it this way, that this power is supplied by the source or the simple harmonic oscillator. So this is equal to the power supplied by the source. Which is the simple harmonic oscillator. So for example, if we have a simple harmonic oscillator operating at a frequency of, let's say, 10 hertz, supplying power P, let's say, in watts, is attached to a rope which has linear mass density, let us say 1.6 grams per centimeter, and is under tension of, let us say, 50 newtons. Let's make this 100 newtons, it'll just be easier to calculate. So this attached to the rope like this creates a transverse wave of amplitude, let's say 1 millimeter. So find the frequency, wavelength, wave speed, and power of the wave. And second part, if the same source, that is the simple harmonic oscillator, operating at same frequency and power, is attached to a rope at tension equal to 25 newtons and linear mass density equal to 1.6 gram per centimeter. Find the frequency, wavelength, wave speed, and amplitude of the wave propagated. Okay, so just try out this question because it will just sort out the aspect of which of the wave properties depends on which of the things, the properties of the medium or the properties of the source, and how all these properties are linked with each other. Okay, so things like v is equal to f lambda, then the relationship of propagation speed with respect to the medium properties tension and mu, and the final thing that we've seen today here, that the relationship of power with respect to all these parameters. So it will just explain how they are interdependent and what actually dictates which one or which determines the quantity of which factor. Anybody completed the calculations? Please let me know.
Sir, going on. So the first part is then the second part is there.
Okay, so just send the answers of the first part first. I'll verify it for you. Okay, good. So I've received all of your answers. Devansh, Viraj, Jagannath, Devansh, the second part also okay. So I'll just verify the answers. First part seems okay for most of you. So it's more or less directly formula based. So you have to remember that the frequency of the wave is basically the frequency of the source. That is the thing which is determined by the source. Okay, so the frequency of the wave will be 10 hertz, but the propagation speed of the wave, that depends on the medium properties. That is purely a property of the medium. So in this case, the propagation speed becomes 100 newtons divided by 1.6 into 10 raised by minus 1. Remember to always convert to kg per meter. Typically, it will be given in gram per centimeter. So this will become 100 by 16 or 50 by 4 or 25 by 2 or 12.5 meters per second. So now you have the relation V is equal to F lambda. Well, this is the property of the medium. This is the property of the source. So this is
But it
lambda
will be
is equal
100 by
to,
4, no?
oh sorry, 100 by 4, my mistake. Yes. 16 is outside, yes. So it will be square root of 16. So 25 meters per second is correct. So lambda will become 25 divided by 10. So 2.5 meters. That is the wavelength. The frequency is 10 hertz. The wave speed is 25 meters per second. And in this case, the amplitude is given to me. In the first part, the amplitude is given. It's producing a wave of amplitude 1 millimeter. And also from this, you can see that the value of omega is 2 pi f. So 20 pi in radians per second. The value of angular wave number k is 2 pi by lambda. So that becomes 2 pi upon 2.5 radians per meter. Or you can write this as 4 pi by 5, whatever. So omega k, all this thing. So basically your wave equation will be something like this. Sine 20 pi t minus 4 pi by 5x plus some phase constant. So this is the only information we don't have in the question to determine the value of phase constant. So we will discuss some questions where phase constant also comes into the picture. In fact, you will find questions like that in HCV also, where you have to determine the phase constant from the initial conditions. So we'll come back to that. But here, this question does not relate to that. That's why the equation of the wave has not been asked. Only these things have been asked. Okay. In fact, what has been asked, I have already put here. Okay. Now the final thing is the power. So for that, we can just use this formula, okay, or half square root t mu omega square t square, whichever choose to use here. So half 1.6 into 10 raised power minus 1 in SI unit mu. Okay, V in SI unit is 25 meters per second. Omega again in SI unit is 20 pi, and amplitude in SI unit is 1 into 10 raised power minus 3 square. So this, the power that we'll get will be in watts. Okay. So you can see that it is 0.8 into 25 into 4 pi square, right, into 10 raised power. We have 2 from here, minus 1 from here, and we have minus 6 from here. So 100. So we can take pi square as almost, right. So 0.8 into 25 into 4, that's 100 into 10 into 10 raised by कितना हो गया minus 7 plus 2, so minus 5. So 0.8 into 10 raised power minus 2 watts. Or you can say it is 8 milliwatts. Approximate 8 milliwatts. Okay. Taking pi square as 10. Or we can say that it is 8 pi square by 10 milliwatts. So just check my final calculation after just multiplying the quantities, but the substitution is this way. You have to remember to substitute everything in SI units in the formula. Okay, now second part, remember what we are doing. We are keeping the power of the source the same. Power of the source is remaining this 8 pi square by 10, or approximately 8 milliwatts. We're keeping the frequency of the source the same, 10 hertz. Okay, so these properties of the source are remaining the same, but the medium is now changing to a new tension of 25 newtons, while the linear mass density remains 1.6 gram per centimeter. So what all that will affect? The wave speed will change, because this has undergone a change. This medium property has undergone a change, whereas rest of the things are same as before. Okay, so wave speed changes. So accordingly, lambda changes, and accordingly, the value of power will change. I mean, the power is remaining the same, the amplitude will change. Whereas power remains the same as before, frequency remains the same as before. So you can see that the wave speed, now the tension I made it 1/4, so the wave speed should become half. So it should become 12.5 meters per second in the second part. So accordingly, the wavelength will also become half, because it is V by F. Frequency is remaining the same, so wavelength would have changed to half of what it was. So it will become 1.25 meters, whereas the frequency remains the same of 10 hertz. So omega remains the same of 20 pi radians per second, whereas angular wave number, this changes. Okay, Jagannath, very good. I'll just verify your answer. Now the power, so this power is remaining the same. It's remaining 8 pi square by 10. This is also remaining the same, 1.6 into 10 raised to power minus 1. But what has changed is the wave speed. It has become half of what it was. Okay. Omega has remained the same, 20 pi square. So if wave speed has become half of what it was, you can see that A square would have doubled. So A will now become root 2 times what the amplitude was earlier. So it will be root 2 millimeters. So there's no need to complete this calculation actually. You can understand it this way, that V1 by V2 will become square root of T1 by T2, because tension has changed from T1 to T2. Okay. And everything else has remained the same. Frequency is same. So lambda 1 by lambda 2 will be equal to V1 by V2, the square root of T1 by T2. And power is remained the same. So power is proportional to V into A square. So A1 by A2 squared will become V2 by V1. Which is square root of T2 by 2. So you can use this relationship directly, and this relationship directly, and this relationship directly to get these new quantities. This one, this one, this one. Rest the things are remaining the same. Okay, so hope this clarifies this important point. Please let me know in case of any doubt or confusion. Okay, very good, Devansh. So waves in that sense is a bit of a chapter like heat and thermodynamics. If your fundamentals are clear and if you understand the derivation of the formulae, okay, then you'll be very clear about how to apply it, and you don't have to put too much effort to memorize the formulae. You just understand them and understand how they're derived, so you'll be able to do the questions quite smoothly. And then the mathematical part of the question is not so complex like mechanics and all. So it's that way a scoring thing. The only thing is there's always a tendency to make conceptual mistakes. If you try and just memorize the formula without understanding the derivations, then you can always make conceptual mistakes in especially the JEE type of questions. Okay. Both JEE mains and advanced. So be careful about that. Okay. Now we go back a little further into the fundamentals before we move ahead. And the fundamentals now we are going to discuss is about the general equation. So far we've discussed about harmonic waves. So general equation of a one-dimensional uh, transverse wave. It need not be a harmonic wave. Harmonic wave is a special case of that. Okay, so let's understand that. So before that, we will look a little bit at graph transformation concept. Okay. That is, if you have a graph of y as a function of x, looks like a particular shape, okay, let's say, and now we want to shift that shape. So how we mathematically deal with it to shift the shape? Okay. So the original function graph is like this: y is equal to fx. But now what I want to do is I want to shift this to this. I want to shift it without changing the shape. I want to just shift this graph by, let's say, d units along the positive x-axis. So what I have to do, I have to replace x with x minus d. So I'm sure you'll be aware of this. So just for example, you know that the graph of, let's say, y is equal to x squared looks like this. So if I make it y is equal to x minus 1 whole square, the vertex shifts to the point 1 comma 0. Or for that matter, if I make it y is equal to x plus 1 whole square, it will shift like this. If I want to make the graph shift towards the left by d units, then I should make it x plus d units. So this is shifting by t. Okay. So now another example of this is that suppose I have the function, like let's say I've got so I've got the function e raised power minus x squared. That looks something like this. Okay. So now if I do this, suppose this is, so this peak has shifted to the point 2. Yeah, so this whole square is not there. That was actually for. Now, similarly, if you look at an example like this, y is equal to, and in comparison to this, I want to, so in this, let's say y is in millimeters, okay, and x is in centimeters. Now I want to shift this by 2 millimeters towards the positive x direction. Okay. So what will be the new equation? Okay, and plot the graph. So just try this out, we'll discuss. So you start with this function, which is y is some amplitude into sine pi by 2x. Let's say amplitude is also given to us. Amplitude is 4 millimeters, let's say. Okay. So y is in millimeters, but x is in centimeters. Okay. Sorry, so x is in centimeters, so I want to shift the graph also by centimeters, not by. So x is in centimeters, and I want to shift the graph by 2 centimeters, not millimeters, towards the positive x direction. So what will be the equation that we'll have, and plot that equation, plot the graph for that equation. Okay, so just try this out, we'll discuss in a moment. Yes, Jagannath, very good. Now the thing is, I will just plot the two graphs in detail. Your equation is correct. Okay. And obviously, do not send me the graphs, so I'll just show it to you and you can verify your result. Okay. So we had the equation to begin with that this is a sine pi by 2x, where a was 4 millimeters and x was in centimeters. So let's start by looking at the graph of this function. So you can even think of this like a snapshot of a particular wave at a particular time. So for example, if it was a wave of the type kx minus omega t at t equal to 0, it would be like this, and k's value is pi by 2x. But anyhow, we are looking at the snapshot.
Sinusoidal.
Sorry, come again, beta.
So it will be a sinusoidal wave.
It will be a sine wave or a sinusoidal curve. Okay, and like it will be such that you can see that it will have a wavelength effectively of how much? Have a wavelength of 4 centimeters, right? This point here, this will be 4, this will be 2, reaches the maxima at 1. So this thing is then repeated. Okay? And this maxima here is 4 millimeters, this minima is minus 4 millimeters. So this y is in millimeters, this x is in centimeters. Now I said I wanted to shift this by a distance of 2 centimeters. So shifting it by a distance of 2 centimeters means that I want to make the graph now like this. So of course this graph has a span on the negative side also. So let's also keep that into account. So let's span like this also. Minus 1, minus 2. So when I want to shift this, you'll see that this whole thing shifts like this. So it should become so visually this is what it will look like when we shift it by 2 units or 2
Sorry,
centimeters.
so 2 में वो negative.
It will become like a minus sign graph actually. So I've shifted it by delta x equal to plus 2 centimeters. So the equation of transformation when I do, it should become like this. It should be a sine pi by 2 into x minus 2, right? To become like this. So you can see that that is y is equal to a sine pi by 2x minus pi is the same thing as minus a sine pi by 2x. So you can see this totally makes sense when we're doing something like this. So now getting back to the general concept. Now, physics-wise, when we write an equation of y as a function of x, okay, in maths, when we write an equation y is equal to fx, x is also a number and y is also a number. So we don't worry about dimensions. Okay, but in physics, if we write y as a function of x, okay, x is a parameter. So it has units and dimensions. Okay, and y is also a parameter. So typically we'll write the equation like this. Y is equal to f of k into x. So that k into x is a number, which is the argument of the function. So it should be dimensionless. And again, there should be some constant into that so that y also has some dimension. I'll just explain this with an example or two and it will become clear to you. Okay. So A is also where K is a constant, but it has dimension of inverse of the dimension of X. Whatever dimension X is having, it will have inverse of that. Okay, and A is also a constant, such that dimension of Y becomes dimension of A. Okay. So what I'm trying to say here is that maths wise we can write an equation y is equal to e raised power minus x is fine, because x is a number and y is a number. Okay. But if x is suppose a length, so dimension of x is L, then y is equal to e raised power minus x is a wrong equation. Okay. Or at least there's a hidden one over here, because the power of e has to be a pure number. Otherwise, it doesn't make sense. So the equation should typically be written as y is equal to some constant into e raised power minus of some constant into x, where k into x is dimensionless. It's a pure number. So if x is in centimeters, then k is a constant in centimeter inverse. And similarly, if y is in some other unit, let's say millimeter, then a has to be in millimeters, because a is also constant. So like that. Okay. So this is just a general thing you keep in mind. Okay. So when we write a physics equation such that you're representing displacement along the y-axis. So suppose y is, so here y is displacement along y-axis, and x is the position on the x-axis. So both are having dimension of length. Then we cannot represent it as a function like that. We have to represent y as something like this. The argument of the function has to be k into x, where k is a constant. So suppose that is like this. Okay. So now if I want to shift that like this by a distance delta x, then I have to transform it as this. Okay. And if I want it to be a moving function, such that delta x by delta t is a constant velocity, it's a constant propagation speed, then what I have to do is I have to write this as this. Now you can see that this becomes a traveling function. Becomes a traveling function. Its graph is a shape that is constantly shifting, propagating at t equal to delta x by delta t along the x-axis. So in general, any equation of the type this is the general equation of a traveling shape, where the traveling speed is either minus or plus of omega by k. Okay, so if the sign between these two terms, so this is actually like this. This term is af of k into x plus minus delta x, where now our delta x should be equal to vt. Okay, so kx plus minus delta x can be written as omega t x, where omega is this term. So what I will do is I'll just separate out this part because it was, I'll write it out as a separate note, okay, that we don't confuse it with this over here.
So the example of y to the power y is equals to e to the power x is for this one. This is one.
Sorry, the example?
You given for the y is equals to e to the power x. It's for this
That,
note. No?
yeah, it's, this is also part of this note. So for this note only, I'm giving a physical example of this, where suppose we have this function where x is a length, no? So it's, so that's why we cannot write it like this. Okay. So in maths this is okay, but in physics we have to modify that whole thing a little bit.
Can you show the graph?
Yeah, I'll show the graph. Just a moment. Okay, so coming back, this graph was the last question. You want to review the graph of that question I had given you, that sine pi by 2x1 or the
No, no, sir, the
transform?
note transfer.
Okay, so to understand the transformation partner first, just go through this note first. Okay, then we'll come back to this transformation. So make sure you understand in this note the concept of dimensionality in a physics equation as opposed to a maths equation where there's no dimensionality involved. So when we write a maths equation, it's okay to write y as a function of x, just like that, because x and y are both numbers. Okay. But in physics, when we write y as a function of x, we have to make some modification because, okay, we have to modify it like this. And for example, that constant can be 1 also, can have a value of 1, but then it will have a dimension. Okay. But that k will have a dimension which will be inverse of the dimension of x. So for example, we can have an equation like this, that y is equal to sine x, where y is in, let's say, millimeters and x is in centimeters. But then we understand that actually this equation is y is equal to a sine x, a sine kx, where k's value is 1 radian per centimeter and a's value is 1 millimeter. Okay. Because otherwise this equation doesn't make any sense. Mathematically, sine x is a dimensionless term. So how can y be in millimeters? Similarly, x is a dimension, should be a dimensionless term. So how can it be expressed in centimeters? So even if we are writing the equation y is equal to sine x, it means that there is a constant 1 into x, where that 1 has a dimension of radian per centimeter. Only then the question makes sense. Only then the equation makes sense. Yeah, Jagannath, I'll go back to the traveling one. So actually the sequence is opposite. That's why I'm showing you this first. Okay. So understand the difference between writing a physics equation between y and x, where y and x have both got units and dimensions, versus writing a mathematical equations where y and x are pure numbers. So when we write this function like this, the argument of the function is kx, and that argument is a dimensionless term. So k has to be a constant which has the dimension of whatever x's dimension is to the power -1, or whatever x's unit is, it has to have the inverse of that. So suppose x is, let's say, a velocity in meters per second, then k has to be having a value in second per meter, so that k into x becomes dimensionless and unitless.
Yes.
Okay, so now once you understood this, so when we are representing a relationship between y and x as a physics equation, okay, so let us say y is a displacement along the y-axis and x is the position on the x-axis. So you want to show that as a snapshot picture at a particular time. Okay, so it has to be this sort of a function. It has to be a function of some term k into x, where k is a constant which has dimension of length inverse. Here k has to have dimension of length inverse because x is in length, and a also has to be a constant which has dimension of length because y is a displacement, so it has dimension length. Okay, so now if I want this to shift by a distance delta x, I should replace x with what? I should replace x with x minus delta x along the positive x direction if I wanted to shift. Similarly, if I wanted to shift along the negative x direction, I should replace x with x plus delta x. Okay. Now,
Yes.
if I want to make this a continuously moving function, that means this delta x should be varying with time like this. Now, delta x should be some velocity into delta t. Okay. So at time t, that delta x should be vt. So if you just look at this function now that we written, the transformed function is f of k into x minus delta x. This is shifted by delta x along the positive x-axis. But that shift delta x, if I just make it v into t, that means it's shifting at a uniform rate of v along the x-axis. Okay. So this becomes a traveling function now, where the graph is propagating at this rate along the x-axis.
Can you repeat that one? What happened?
देखो suppose मेरे पास एक ऐसा
traveling
y is equal to 2 into e raised power minus 3x square. Suppose I have this function. Okay. So it's going to look something like this. It's a peak like this over here. Okay. Now if I
Yes.
replace x with x minus 1 or something. Okay. So it should look like this, x minus 1 whole square. So now it becomes a peak which is over here at x equal to
At
1.
1.
So it has traveled by delta x equal to 1. Okay. But now if I want it to travel at a constant rate, so that at some time t, the peak should be somewhere here. Let's say. I want that at time t, the peak should be at, let's say, x equal to 2t, because it's traveling at a speed of v equal to 2 meters per second over. So then what should happen? I should replace this 1 over here. The delta x should become what? At time t, the delta x should be v into t. So in this case, it should be 2v. So the function should be what? Y is equal to 2 e raised power minus 3. Instead of x, I have x minus 2t and this whole thing squared. So now this function represents what? It represents a pulse like this or a peak like this, which is traveling at a constant rate of 2 meters per second. Okay. So that thing only in generalized form we've written over here. This is an example of that. We've written that in generalized. Is it clear now?
Yes, sir.
So अगर मैं y is equal to f of kx में x को x minus delta x से replace कर देता हूँ. So the whole graph is shifted by delta x. So like that, if I now think delta x is some constant v into t, that means it's shifting periodically, with time. It's shifting uniformly with respect to time. So it instead of a fixed stationary shape, it becomes a moving shape. Now, if we track that graph with respect to time, we are seeing that shape is remaining fixed, but it's traveling along the x-axis. Okay. So hence this becomes the general equation of a traveling shape or a traveling graph. So physically, if here y is the displacement of medium particles in the transverse direction, and x-axis is basically the orientation of the string when all the particles are at the mean position, then this traveling shape, it represents what? It represents a traveling wave. Now, if the shape of that wave happens to be a sinusoidal shape, because that function f is a sine function, then it's a harmonic traveling wave. But not every wave needs to be harmonic, because harmonic wave will come from a source which is harmonic. But suppose our source is not harmonic, it is something else, then the shape will change, but the form of the equation will remain the same. Okay, so hope this point is clear over here. So with this, we come to, yeah, I'll go back here. General equation of a one-dimensional transverse wave. The general equation is like this. Y is some kind of function. Assume A is included within that function. Okay. Of kx plus minus of omega t. And it doesn't matter what order we write it in. We can write it as omega t plus minus kx also, where the propagation velocity v is minus or plus of omega by k, which means that basically if the sign between kx and omega t is plus, then the propagation velocity is along the negative x-axis. If the sign is minus, then it's along the positive x-axis. But now there are two qualifiers on this function also. And because, so where, what does y represent? Y represents the transverse displacement, right, of a particle, of a medium particle at x equal to x, at time t equal to t. Okay. So because it represents that, so therefore y must be a continuous function. It should not have discontinuity. So this function f must be continuous for all x and t. And secondly, particle velocity del y by del t will become partial differentiation of this function. So that will become plus or minus omega into derivative of this function. Now this partial derivative represents a physical quantity, that is the particle velocity. Okay, so it must have continuity, which basically means that f prime must be a continuous function for all x and t. Okay. So which means that the function f has to be differentiable. You've done limits, continuity, and differentiability in maths?
No, sir.
No, sir.
Okay. So you'll do this at a slightly later stage, so you'll understand. But I'll give you with examples where you'll understand what is the meaning of differentiability and all that. And similarly, del 2y by del t square, this represents particle acceleration. So this is going to be now minus omega square f double prime, or sorry, plus minus, because it depends on, oh, wait, it will not be plus minus, it will just be omega square by mistake. So it is omega square f double prime kx plus minus omega t. So because this represents particle acceleration, which is a physical quantity, so del 2y by del t square or f double prime must also be continuous. So that means the function's second derivative should be continuous. So we summarize all this by saying that y should be a function of this type, that the argument of the function is linear with respect to x and t, and the function f should be continuous and twice differentiable. That means first derivative and second derivative are both continuous for all x and t. So there's an added condition that not only the function's argument, the argument of the function should be of the type kx plus or minus omega t. So it should be linear in x and t. Okay, so y is basically, think of it as something like this, where this should be linear in x and t. Like this, okay. But in addition to that, it should also be twice differentiable. That is, the function should be continuous for all x and t, and it should be differentiable. Its derivative should exist, and its second derivative should also exist at all values of x and t. So this
It
is,
should not be a constant like.
sorry, come again.
If the first derivative become a constant, it is possible.
If we, sorry,
मतलब constant हो गया तो चलेगा क्या? First derivative.
I didn't
first
understand your
derivative.
question. What about the constant?
मतलब differentiate करने के बाद से अगर हमें constant value मिलता है velocity.
It's possible. It could be that the first derivative is a constant and the second derivative is therefore 0. Even that is possible. Okay, but then it should, that differentiated term should be continuous. So constant is also a continuous function.
Okay.
So I'll give you an example or two, and you'll understand that what we mean by this continuity thing. Okay, but I think somebody wanted to write down this earlier part. Is it
Yes.
this part, right?
Above graph
The
also.
general equation of
Yes.
the general equation of traveling one, no?
Yes. Yes, sir.
Okay, so this is the same thing, but it's summarized now, and plus it's summarized with the added context that if that function is representing a traveling wave, then y represents a physical parameter. So y should be continuous for all x and t. Similarly, del y by del t represents a physical parameter of particle velocity. So del y by del t also has to be continuous. So that means in maths language, we say that when the derivative of a function is continuous, that means the function is differentiable. And similarly, if the second derivative of the function is also continuous, it means that the function is twice differentiable. Hence, in final conclusion, what we say that not only the argument of the function has to be of the type kx plus minus omega t, but the function f has to be continuous and twice differentiable for its entire domain. That means the value of the function, the value of its derivative, and the value of its second derivative must be well defined for all values of x at all values of time. So for example, we cannot take a function like a tan function. No, because you know that whenever the argument of tan function becomes of that odd multiple pi by 2, it becomes an undefined quantity. No? And derivative of tan is sec square. So even sec square is 1 upon cos square. So it becomes undefined wherever the argument is such that cos becomes 0. Yes, I'll come to that part, Jagannath. Okay. Let people just finish writing down the top part, then we'll discuss that also.
So can you show the below part?
Yeah, just showing this part. Okay. So for example, this function represents a traveling wave. Because basically it is of the type y is equal to a sine theta, where theta is linear in x and t. And also sine function is continuous. f prime or cos function is continuous, and double prime or minus sign function is also continuous. But for example, if we had a function like this, y is equal to, let's say, 20 tan of pi by 2 x minus, let's say, 50 pi t. We had a function like this. So this is a function of the type kx minus omega t. That's okay. But f is not continuous because f is the tan function, and you can see that this function is discontinuous at theta equal to pi by 2, 3 pi by 2, 5 pi by 2, etc. Or for that matter, if we have a function of the type so this is again y is a function of kx minus omega t, or even if we make it plus, it's fine. So the argument is linear in x and t, but for this term 5x plus 3t being 0, y is undefined. Okay. So therefore, it is not continuous for all x and t. So therefore, this cannot represent a traveling wave. But if we were to modify this in such a way to something like this, if I make this y is equal to 2 plus, let's say, some constant like 2 only, plus 5x plus 3t whole square. Now you can see that this represents a wave. This is continuous, okay, and twice differentiable. Okay. It would be a very lengthy process to show it, but if you differentiate this function twice also, both the derivatives will also be, the first derivative and the second derivative will also be continuous. Because you can see that this function has now become of the type this, okay, where theta is 5x plus 3t. So it is kx plus omega t. And the denominator, which is 5 plus theta square, or whatever, 2 plus theta square, is always greater than equal to 2 for all theta. Now there's no problem of discontinuity. So this now represents a traveling wave. Whereas the above one did not. If we modify this function to this by just putting this extra term in the denominator, you can see that now this represents traveling one-dimensional wave. So firstly, there are these type of questions which you might deal with at JEE Advanced level in particular, that some example functions are given to you and you are asked to select that which one represents a traveling wave. So you can see that, for example, if I have one option like this, one option like this, one option like this, then let's say I have another option like this, that y is equal to 10 sine pi x square minus 2 pi t. So again, you can see that this does not represent a traveling function because it is not linear in x and t. This does not represent because the argument of the function is pi x square plus minus 2 pi t or whatever. Okay. So this is non-linear. So it now does not represent a traveling wave. So basically you have to see that the function should satisfy the criterion that we had written earlier, that its argument should be linear in x and t, and plus it should be continuous as well as twice differentiable for all values of x and t which are within your domain. Okay, so there is a bit of discussion of this in H.C. Verma as well as in Resnick-Haddad. And there are a few questions in H.C. Verma of this type also, which I'm showing you, that whether a given function represents a wave or not based on this criteria. So you can try those out before the next lecture we have. I think we have another lecture this week on Friday or Thursday, one of those days. So we'll discuss further from this point, and we'll start looking into the next part of waves, which will be superposition of waves. That's it for today's session, people. Wish you all the best and have a nice day.
Thank you, sir. Bye.